So let's begin with session 6, sequences, algebra of limits. Okay, so here we are going to prove for the sequence, convergency of the sequence in case of four operations, that is addition, subtraction, multiplication and division. So let us consider the xn and yn be any two convergent sequence, and since they both are the convergent sequence, it satisfies the definition of the convergent sequence, that is limit n tending to infinity xn is L and limit n tending to infinity yn is M. So it satisfies the definition. Then what we are supposed to prove? Then limit n tending to infinity xn plus yn is, I have to show that it is L plus M, and limit n tending to infinity xn minus yn is L minus M. Similarly, in the case of multiplication, I need to show L dot M, and in the case of division, I should show it as L by M, where the denominator is a non-zero quantity. So let's start proving this part. The first part we will take. What do we know? First of all, that it is a convergent sequence. So limit n tending to infinity xn is L and limit n tending to infinity yn is M. We know by the definition of the convergent sequence. Now here let me consider m1 and m2 belonging to my natural numbers at capital N, such that what is the condition that it is satisfying is modulus of xn minus L is less than epsilon by 2. This is for all n greater than m1. So it is satisfying this modulus of xn minus L is less than epsilon by 2. Similarly, for the other convergent sequence, I will be able to write the modulus like this: yn minus M is less than epsilon by 2. This is for all n greater than m2. Whatever we consider two quantities m1 and m2, which is there in my natural number set. Now here let me take capital M, that will be the max of m1 and m2. Now since we know that modulus of xn minus L is less than epsilon by 2 and modulus of yn minus M is less than epsilon by 2, this is for all n greater than M. It satisfies this condition, right? So now let me consider modulus of xn plus yn plus of L plus M. Let me consider this. So what do I get? I get it here as that is equal to xn minus L plus of yn minus M. So how did I get this? Sorry, here it should be a minus sign. So xn minus L plus of yn minus M. Okay, so what do I get? This is less than or equal to, if I am going to write this inequality, modulus of xn minus L plus modulus of yn minus M. So what is this? Actually this quantity is less than my epsilon by 2 and this is less than epsilon by 2. So epsilon by 2 plus epsilon by 2 is less than epsilon. This is for all n greater than M, for all n greater than M. And therefore, this is satisfying the condition, that is xn plus yn minus of L plus M is less than epsilon, and hence it satisfies the positive quantity, for the positive quantity, that is limit n tending to infinity xn plus yn is equal to L plus M. So it is a positive quantity holds and it is L plus M. Similarly, try to solve for limit n tending to infinity xn minus yn is L minus M. Try to solve for this on the similar lines. You can do this. This is the second one, and third one is what we need to show. It holds for multiplication. See, third one is limit n tending to infinity xn dot yn is L dot m. We need to prove the multiplication holds good here. So now let's start here the proof for the third one. That is, since we know that yn is convergent sequence, right? Yn is convergent. If it is convergent, it is bounded. It is convergent, it is bounded. Therefore, there exists a real number k such that modulus of yn is less than capital K. This is for all n belonging to n and n is greater than m. Okay, so now limit n tending to infinity xn is equal to L. This is the convergency of the xn, we know by definition. This is for all epsilon greater than 0 where m1 belonging to n such that it satisfies the condition modulus of xn minus L is less than epsilon by 2k. This is for all n greater than m1. We choose epsilon by 2k, which is a positive smaller quantity, a very small quantity that we choose. It is there in xn minus L. So on the similar lines, let me try for limit n tending to infinity yn is m. This is for all epsilon greater than 0. There exists some m2 quantity in the natural number set n such that modulus of yn minus m is less than epsilon by 2 into modulus of L. This is for all n greater than m2. Okay. Now let me take m, capital M. That is the max of m1 and m2. So now here we have chosen, here it is as epsilon by 2k and epsilon by 2 modulus of L. So now let's see how to combine this. So modulus of xn minus n is less than epsilon by 2k, and we know modulus of yn minus m is less than epsilon by 2 into modulus of L. This is for all n greater than m. Since we have considered m as the maximum of m1 and m2, I am able to write this. Now let me consider, since we need to prove the operation multiplication with the convergence sequence, let me solve this. So modulus of xn dot yn minus L dot m. So what is this? Let me add and subtract L-yn, the other side of this modulus. So what do I get? xn-yn minus L-yn, okay, plus L-yn minus Lm. So here I can take yn common, so it is xn minus L, plus here I can take L common, so it is yn minus m. Now applying the inequality for this and separating the terms, what do I get? Modulus of yn dot modulus of xn minus L plus modulus of L into modulus of yn minus m. Now which is less than? What is modulus of yn? Modulus of yn is k. We know modulus of yn is k. So let us write this as k. Dot, what is modulus of xn minus L? We know it is epsilon by 2k. Plus modulus of L is as it is. What is modulus of yn minus m is epsilon by 2l. So it gets cancelled. So finally we have epsilon by 2, that is less than epsilon. This is for all n greater than m. So modulus of xn dot yn minus L dot m is less than epsilon. This is for all n greater than n. Okay.